We will start studying the chemical bond by just considering that a chemical bond is formed when two atoms meet. Depending on the identity of those two atoms, depending on where they are, if they are a nonmetal or they are a metal, the characteristics of that bond will be very different. So what possibilities do we have if we just split the periodic table in two, we split them between metals and nonmetals? There's three possible combinations. The first combination is when a metal meets with a nonmetal. The second combination is a nonmetal with a nonmetal. And the third and final combination is a metal with a metal. Depending on these combinations, you'll have different kinds of chemical bonds. Let's remember that nonmetals are highly electronegative, so that means that they will tend to keep their electrons. They keep their electrons, and the metals, mostly on more to the left and low that you go into the periodic table, the more metal it will be. They are less electronegative, and they are willing, or not so, no atom is willing to give away the electrons, but they do not keep the electrons as much, so they will let the electrons out. Okay, they will lose the electrons. Okay, let's put it maybe better. Lose the electrons. They tend to lose the electrons. So when a metal meets with a nonmetal, it's clear then that there has to be a transfer of electrons between the metal to the nonmetal. The metal has a lower electronegativity, therefore it will lose the electrons because the nonmetal wants those electrons. When the nonmetal meets with the nonmetal, both of them, the nonmetal meets with the nonmetal, what you have is the so-called a covalent bond, because it means that there has to be a sharing of electrons. And when a metal is bound to another metal, what you have is so-called, of course, metallic bonding. Okay, the kind of bond that you will have, you can think of it as if this were business. The ionic bonding, of course, could be like a theft of electrons, because the nonmetal keeps all of the electrons, not all, but whatever it's being exchanged. For covalent bonding, there has to be a partnership, because they actually share the electrons. And for the metals, I call it the communism of electrons, because suddenly now the electrons are not associated to any metal at all. They will form a pool. The electrons will be in a pool of electrons that do not belong to any specific metal or to any specific nucleus. So that also, of course, affects the kind of bonding, and also a very important aspect, the directionality and the strength of the bond. So when an ionic bond is formed, once there is a transfer of the electrons, you could say that what is left is just a charge. So for sodium chloride, table salt, what's left is just the cation and the anion. Therefore, this kind of bonding is not directional. What do I mean by that? Well, being sodium just a positive charge, it can interact with as many chlorides as it has around, and there's another chloride here, and of course it would be one above and one in front if it weren't because this sodium is on the edge of this cube. So ionic bonds are not directional. They do not have a preference, because the charges are spherical, so they interact with any anion around them. It's very different from covalent bonding. Covalent bonding is directional, because when chlorine and bromium form a bond, these electrons have to be in a specific direction, in the direction of the atom to which it's bound. This means that this chlorine does not interact with this, or does not interact as strongly with this other bromine, and this other bromine does not interact with this other chlorine. That means, therefore, that the covalent bonding is directional. And that will be important because the covalent bonding will form molecules. Notice that the ionic bonding will not form molecules. Ionic bonding will form a lattice of cations and anions arranged in the space just as packed as possible. Okay. And finally, the metallic bonding also is non-directional, because the electrons are not shared, or not necessarily shared with a specific another atom. what we will say is that there is a pool of electrons that can move from atom to atom. This is why metals are so good at conducting electricity, because those electrons are free to move from higher potential to lower potential of the electric current. So let's see if we can just, by looking at the formula, we can identify what kind of bonding in a compound there is. So in this case, you have to state the type of bonding, either ionic, covalent, or metallic, that you would expect in these compounds. And here I'm listing some instructions. You are then welcome to stop the video and read through them, but we will just solve this exercise on the fly. So cesium fluoride, notice that cesium is a metal, and fluoride is the king of the nonmetals, the most electronegative of the periodic table. This means that this is an ionic bond. Okay. In this case, nitrogen is bound to another nitrogen. This is a nonmetal with itself, and therefore a nonmetal. This has to be covalent. Sodium here, notice there's only one atom, but because it's solid, it means that sodium is bound to sodium all over. This is a metallic compound, and therefore bound to itself, it will form a metallic bond. Hydrogen sulfide, here the position of hydrogen may be misleading. You may think, well, hydrogen is on the left part of the periodic table. Let me tell you, this is an exception. We will treat hydrogen as a nonmetal. A nonmetal is in this case bound to sulfur, which is not a nonmetal. This is a covalent bond. And this is a molecule. Okay, notice that this is not a molecule. This is a lattice of ions, a lattice of cations and anions placed on a strong network of charges. And finally, magnesium chloride. Magnesium is a nonmetal. Sorry, magnesium is a metal based on the position on the periodic table, and chlorine is a nonmetal. What you have here is another ionic compound. Okay, we'll practice more.